There are two processes inside of your body that are used to make ATP. The electron transport chain, which releases energy from certain high energy molecules, as well as chemiosmosis, which is using that energy release and using the transport of these charged molecules to synthesize ATP, which is the universal energy currency. ATP, it is the thing that makes your muscles move. It is the thing that means that you can walk. It basically, all your cells use it to be able to continue functioning, because ATP is needed for so many high energy metabolic reactions, as well as the fact that it's needed to increase the intensity of those high energy metabolic reactions, such as Krebs cycle, glycolysis, oxidation, etc., all that sort of stuff. It's an incredibly important molecule, and despite that, I have always struggled to understand the stage in which it's actually synthesized. You've got glycolysis and you've got the Krebs cycle. I've explained both of those in detail in separate videos, but I've never really explained oxidative phosphorylation in like a specific video. I've talked about how all the different things that are inside the generic respiration equation are involved in some way, shape or form in the process of producing ATP and lots of energy, but that was like the most basic explanation of this process that I could give. But it is a lot more detailed, and I've always wanted to understand it, but never really been able to, because all the images, I'm quite a visual person, all the images that I've been able to look at, they've all been the same style of thing, but that's also been quite a hard thing to understand in a weird sort of way. But I think I'm getting there. This was like the video that I did in this particular bulking, recording, scripting, video session, etc. that took the most amount of research and the most amount of time to script, and potentially the most amount of time to record too, because there is quite a bit of details to go through. But the electron transport chain starts with high energy reduced electron carrier molecules such as NADH and FADH2. If they're not already in the mitochondria, being transported to the mitochondria, and that is where this process begins. These are reduced molecules, meaning they contain electrons. Reduction is the gain of electrons, so these molecules have been reduced. Say NAD+. NAD+ has been reduced to form NADH, and NADH would have to be oxidized to form NAD+. We're going to talk about how NADH goes through the electron transport chain first, and how the electrons are transported between certain complexes. There is probably 10 times more detail than I'm going to cover in this video, but I do want to give you a basic understanding that you'd probably get inside of like a school, which would take like an hour or something for you to fully grasp. But I want to try to give you an understanding that someone like that would have in however long it's going to take me to record this video. So the way that NADH is then oxidized to actually release electrons and protons is NADH will be catalyzed by NADH dehydrogenase, aka complex 1. This will form NAD+, as well as 2E-, meaning 2 electrons, and 2H+, meaning 2 protons. I've got an image up on screen which is able to explain all of this, so I've not really had to put different images in different places and stuff like that. But if you look at the differences between the two molecules, you'll notice that in NAD+, one of the nitrogens has an extra bond, which means that it has a positive charge. Now, NADH doesn't have this positive charge because one of these the nitrogen ends up not having a positive charge in NADH because it has extra nitrogens, which means that the carbon doesn't have to bond to that nitrogen and it can bond to a hydrogen instead. And yeah, loads and loads of other stuff happens, which means that when you transfer NADH to NAD+, you end up getting rid of two electrons and 2 protons because of the fact that the structure changes. And hopefully this image explains it well enough, and if you're a visual learner like me, it will probably hopefully just click instantly and you'll finally understand how this specific reaction works, because I never quite understood how it worked before, despite talking about these molecules being coenzymes so often. So we'll get to where these electrons and protons go in a minute, but we'll get onto the other high energy molecule now, which is FADH2. FADH2, again, the image is going to be up on screen. It goes through complex 2, another protein. This will mean that it also loses 2 protons and 2 electrons. If you look at the differences between the two structures, again, you'll be able to see that the removal of double bonds between things like carbon-carbon and carbon-nitrogen means that an extra hydrogen can be added onto the molecule. And obviously that means that when you transfer FADH to FAD+, that hydrogen is going to then be gone because the double bond would have reappeared. And that's why you get these protons, because hydrogen isn't the most electronegative element, so it's not going to keep its electrons and it's going to just roam around free as a proton without any electrons. So when you ever see H+ in any of your school classes or around the internet, just know that is quite literally just a proton, simply put. Now, we'll get on to what the protons do in a minute, but these electrons are passed down in these protein complexes that are tied to the mitochondrial membrane. They will transfer through all these proteins. There's an arrow, there's an image on the screen that I will also show this with. The arrow shows the path of these electrons by binding to certain amino acids in the protein, certain compounds. It goes from a highest energy to the lowest energy. That releases little bits of energy at a time, and then eventually these electrons will reach oxygen, which is the final electron accepts, where these electrons and protons just get dumped. The fact that these electrons have gradually gone from a state of higher energy to lower energy causes then an electrochemical gradient, meaning the protons can be pumped into an intermembranal space through active transport, and I'll get on to what those do in a little bit. But firstly, I'm going to talk about the way that oxygen accepts these two electrons, because oxygen as a molecule, it's double bonded to itself. But the way that this will form water, because if you look at the generic respiration equation, oxygen forms water. Oxygen's a reactant and water is a product. It's a very specific chemical reaction. So the way these electrons are actually dumped onto oxygen, which is the final electron acceptor, is 2 electrons will be added to one molecular oxygen molecule, which will then form 2 O2 minus anions, and then 4 H plus, so 4 protons, which have gone through a process which is actually the thing that produces ATP, but I'll get onto that in a little bit. These will then attach to oxygen's lone pairs to form water. If you imagine O2 minus and 2 H plus being added on, the charges cancel out, right? You've got 2 H plus, so that ends up being a 2 plus charge. You've got 2 minus, which is a 2 minus charge. So henceforth, you end up getting a neutral charge, which is what water is. It's a neutral molecule. It is a polar molecule, so it has dipoles and stuff like that, but that's a bit more complicated. But overall, it is a neutral molecule. It's not ionized or anything like that. Now, the way that the H plus gets from the intermembranal space that we talked about earlier is through a channel known as ATP synthase. Now, because all of these, due to the electrochemical gradient, all of these H plus have been pumped into this membrane space. So there's a very, very high concentration of H plus in this intermembranal space. Then ATP synthase will open up, and all these H plus ions will come rushing through into the mitochondria, and then they'll be dumped into the oxygen, which will be able to transform into water, which is good. But ATP synthase will utilize the charge that these molecules have. H plus, it's charged. If you think of an electron, E minus, that's the thing that goes through the wires when your phone is charging. That is charged. E minus is charged. So H plus, a proton, is equally charged, but it's just positive. So ATP synthase utilizes this flow of charge, which is going to be very quick because of the concentration gradient, and it will synthesize ATP, which is a high energy molecule, and it needs that high energy charge gradient, the flow, which is just going to be so quick to actually synthesize that molecule. And then boom, you can do your bench press, and this will happen at such an incredibly quick rate you won't even notice it. It's going to be increased it's going to have an increase in rate when you are doing exercise, but when you are not doing exercise, when you're just going around your day-to-day life, it's going to have like a basal sort of rate, which I'm not really going to bother explaining right now. But that's about all I wanted to say for this video. That is the process of oxidative phosphorylation. I hope you understood some of the images that I put on the screen, like full screen and stuff, so you could really take in how this process actually worked. And I would have drawn arrows and done my own little weird things, maybe hand signals, etc., to help you understand it. But with that, I recommend subscribing, because I like this community of young tribal people who are willing to improve themselves. So much more than they already have, and good luck.